Hello everyone. Welcome back to this lecture series on Design of RCC Structures. So far in the Design of RCC Structures course, we have studied the design of beams, slabs, staircase, flanged beams, continuous beams and even shear torsion behavior. All these elements primarily resist bending and shear. In today's lecture, we move to another very important structural component, the column, which is the main load carrying vertical member in reinforced concrete buildings. The topic of today's lecture is short columns subjected to axial load designed using the limit state method as per IS 456. Now, a compression member is a structural element that is subjected predominantly to axial compressive forces. In reinforced concrete buildings, compression members are most commonly encountered as columns or pedestals. So columns forms the vertical framing system of a structure which are responsible for transferring the loads from the slabs, beams as well as the upper floors safely down to the foundation. As per IS 456, a column is a compression member whose effective length exceeds 3 times the least lateral dimension. Whereas a pedestal is a compression member whose effective length is less than 3 times its least lateral dimension. So the failure of a column can lead to a progressive collapse, hence column design is extremely critical. Here the columns are classified based on several criteria. So common classifications include short columns and long columns, axially loaded columns and eccentrically loaded columns, tied columns and spiral columns. So here the short columns, how it will be defined as a short column is if the slenderness ratio is less than 12. In other case, if the slenderness ratio is greater than 12 means it is termed as slender or long columns. Once if the type of reinforcements are provided as a tied one, it is called as tied column. In other case, if it is a circular column wherein instead of going with a tied transverse reinforcement, if you are providing the spiral reinforcements means it is called a spiral column. Then regarding the type of loading, if the load is acting exactly on the axis of the cross section, then the column is said to be axially loaded column or concentric loader. In the second case, if the load is having eccentricity with respect to one axis, whereas the other axis, if it is lying on the axis itself, means that type of columns will be subjected to loading with the uniaxial eccentricity or uniaxial bending. And the third case is if the load is having eccentricity with respect to both the axes, then the column will be subjected to biaxial bending. So in this lecture, we focus on short columns which are subjected to axially loaded one. Why short columns are important means short columns fail mainly by material crushing, which can be designed using simple Codal expressions and are very common in low and medium rise buildings. Then the effective length of the column. How the effective length of the column will be computed means it is first based on the type of the bracing. It depends on the end conditions, whether the column is braced or unbraced against the side sway. So IS 456 provides effective length factors for both braced columns as well as unbraced columns separately. This effective column or effective length determines the slenderness ratio, whether the column is short or long, and the applicability of the short column design formula. Now moving on with the braced and the unbraced, braced against sideway and unbraced against the sideway. So in braced columns, the lateral movement is resisted by either shear walls or bracing systems or even the rigid frames. Such columns carry mainly the axial load, which have smaller effective lengths and are less susceptible to buckling. And most building columns are braced columns only. In unbraced columns, lateral displacement is possible. That is what you can see here. The lateral displacement is not available in any of these cases, either at the bottom or at the top. Whereas going on with the unbraced against the side sway, we can experience the lateral displacement. So these columns are more prone to buckling, which have larger effective lengths and require careful stability checks. However, unbraced columns are relatively rare in RCC buildings. Now, regarding the effective length, specifically for braced against the side sway, if both the ends are rotationally fixed, that is fixed column in the sense, the effective length will be 0.5 times the length, that is the unsupported length between the unsupported length of the column. The second case is if one end is rotationally fixed and the other end is free, means the effective length will be 0.7 times the L. The third case is if both the ends are rotationally free, that is both the ends are simple supports, means the effective length will be equal to the unsupported length of the column itself. And final cases, both the ends are partially restrained, will have this condition, LE will be equal to K into L, and K represents, which will be defined with a maximum to the minimum condition of 0.5 to 1. Now regarding the reinforcements, so IS 456 specifies strict limits for longitudinal reinforcements in column. So the minimum steel reinforcement should be greater than or equal to 0.8 times the gross cross-sectional area of the column. And the maximum reinforcement should be less than or equal to 6% of the gross cross-sectional area. The minimum bar diameter will be greater than or equal to 12 mm and it should not be spaced more than 300 mm apart, the center to center distance. And regarding the number of bars, if it is a rectangular cross section or a square cross section, we need to provide a minimum of 4 bars, one at each corner. Whereas if it is a circular column in the sense, we need to provide at least 6 bars, which should be equally spaced along the periphery. Regarding the minimum clear cover, 40 mm should be given, or the bar diameter, whichever is greater, should be provided to the columns ties in general, which can be reduced to 25 mm if the size of the column is less, that is, if it is less than or equal to 200 mm and whose reinforcing bars do not exceed 12 mm. Whereas in case of aggressive environments, it is desirable in the interest of durability to provide increased cover, but in no case this value should exceed 75 mm. Now the proper detailing of the column reinforcement is as important as strength calculation. Next, regarding the transverse reinforcement. So normally transverse reinforcements in the column may be provided as either lateral ties or helical reinforcement. So the functions of transverse reinforcement is to prevent buckling of the longitudinal bars, which will confine the concrete and improve the ductility and load carrying capacity. So the spiral columns can carry higher loads than the tied columns due to better confinement. So regarding the diameter of the lateral ties, so the diameter of the lateral ties should be greater than or equal to 1/4 of the maximum longitudinal diameter of the bar, or otherwise 6 mm, whichever is greater. Regarding the spacing of the lateral ties, the spacing should be less than or equal to the minimum of these 3 conditions. One is the least lateral dimension. Second one is 16 times the diameter of the minimum longitudinal reinforcement. And the third one is in no case it should exceed 300 mm. If it is a helical reinforcement, that is the spirals, the pitch, the diameter we can assume, not like the case of this lateral ties. In case of helical reinforcement, the diameter can be assumed in any way. Whereas the pitch should be less than either 75 mm or 1/6 of the core diameter. In no case, it should be it should not be less than 25 mm or 3 times the diameter of the helical reinforcement. So with this background, let us consider the numerical example 1. Here, we are required to design a rectangular RCC column of size 450 mm by 600 mm, which is subjected to an axial load of 2000 kilonewton under service dead and live loads. The additional data which are provided are unsupported length is 3 meter. The column is braced against side sway. The grade of concrete is M20 and that of steel is Fe415. So this is a typical interior column in a multi-story building. So normally we will calculate the slenderness ratio about both the axes and we'll be checking whether that value is less than 12 or not. Since the column is having an unsupported length of 3 meter, so the slenderness ratio will be calculated 3 meter by 450 mm and 3 meter by 600 mm. In both cases, the slenderness ratio will be less than 12 and therefore this column will be designed as a short column. Now, even in axial loading, perfect axial load is not possible. That is why IS 456 specifies a minimum eccentricity which has to be checked and satisfied. So they are given two conditions. One is the minimum eccentricity along the x direction and the minimum eccentricity along the y direction, in which the formula has been given as unsupported length divided by 500 plus the dimension divided by 30. That is the y direction dimension. Coming on with the y direction, the minimum eccentricity will be calculated as same 1/500th of the unsupported length plus the x direction b divided by 30. So all the values are known, substitute that value, and in no case this value should be exceeding 20 mm in both the directions. If it is exceeding 20, it should be exceeding 20 mm. If it is not exceeding 20 mm in the sense, obviously it is well within the axially loaded case. So we don't need to check the other condition, that is it should be less than 5% of the cross-section dimension. Again, I am repeating, if this value, if any of these value is greater than or if it is less than 20 mm in the sense, this check is not required. Whereas in this case, you can see both the values are exceeding 20 mm. That is why we are checking the 5% of the dimension along the direction. So whatever the D we are taken here, that should be taken in this case. Here B in the sense, that will be taken in this case. So here in this case, you can see 5% of the dimension is 30 mm. Here we calculated is 26, which is less than 30 mm. So this one is satisfied. Similarly, along the y direction, the maximum value is 22.5, whereas the calculated one is 21, which is also well within the permissible limit. Therefore, the code formula for axially loaded short columns can be used in the design. Now, the design of longitudinal reinforcement, this formula has been given. PU will be equal to 0.4 FCK AG plus 0.67 FY minus 0.4 FCK into ASC, where PU is the axial ultimate load acting on the column. AG is the gross area of the column, and then ASC is the area of the steel which will be provided as the longitudinal reinforcement, that is the compression steel. Now, since the service load has been given, that has been multiplied with the 1.5 factor of safety. So 1.5 into 2000 kilonewton, that's why it has been converted in terms of Newton, which will be equal to 0.4. FCK is grade of concrete, which is 20. AG is the gross area of the column, which is 450 mm by 600 mm, that is B into D, plus 0.67 Fy, grade of steel, which is 415, minus 0.4 into FCK is the grade of concrete into AAC. This is what we are supposed to calculate. So solving this equation, we will get the value of AAC as 3111 mm square. And we should check this value should be greater than 0.8% and should be less than 6%. That is the minimum and the maximum percentage of the reinforcement required for the column. Now, we are providing 4 numbers of 25 mm dia and 4 numbers of 20 mm dia bars as the longitudinal reinforcement. So the AST provided is 3220 mm square. So now the percentage of the reinforcement is similar to the beam design, 100 ASC provided divided by the effective area, B into D. So which comes as 1.19 percentage. And this value you can see which is exceeding the minimum condition of 0.8, that is the minimum, and it is also less than 6%, that is the maximum, P max, which is also been given. Right. Therefore, we can provide the same thing. That is 4 numbers of 25 mm dia and 4 numbers of 20 mm dia bars as the longitudinal reinforcement. Now, moving on with the transverse reinforcement, we don't need to go with any design with respect to the lateral ties. Directly, we can provide the diameter and the spacing based on the IS Codal provision. So, as per the IS Codal provision, the lateral tie diameter should be exceeding the minimum of these two, or the maximum of these two. One is 1/4 of the maximum longitudinal diameter, as well as the second case is 6 mm. In no case it should be less than 6 mm. So here we provided the maximum diameter as 25. So 1/4 of the 25 we are getting 6.25 mm. Therefore, we need to provide the lateral tie diameter as greater than 6.25. So in that case, the next diameter of the bar which is available in the market is 8 mm. Then regarding the spacing of the ties, we have 3 conditions. That is, the spacing of the ties should be less than or equal to, one is the dimension, second one is 16 times the minimum longitudinal diameter bar, and third one is 300 mm. So one is the least lateral dimension is 450 mm, 16 times the minimum bar what we provided the longitudinal one is 20 mm. So 16 into 20 we are getting 320, and the minimum case is 300. So the spacing should be the minimum of these 3. So in that case, we can provide 300 mm. Therefore, we can provide 8 mm dia lateral ties at 300 mm centers. This is what is the reinforcement details. We have 450 mm by 600 mm. All the 4 corners being provided with the 25 mm dia bars, and the intermediate being provided with the 20 mm dia bars. And the lateral ties are provided at 300 mm centers, both connecting the periphery as well as a staggered one. The clear cover has been assumed as 40 mm in this case. Now, moving on with the second example, wherein a circular column has been provided. And we are supposed to design a spiral reinforcement. So, the given data are a circular column of 400 mm diameter, which has been subjected to an factored axial load of 1500 kilonewton. The unsupported length is given as 3.3 meter. The column is braced against side sway, and the concrete is M25 and the steel is Fe415. Now, why spiral columns are studied in the sense, as we discussed, spiral columns provide higher strength, show better ductility, and are preferred in seismic regions. As like the previous problem, the short column condition is satisfied. That is, the slenderness ratio, which is 3.3 meter divided by 400, you'll be getting that value is less than 12. Obviously, it has to be designed as a short column. Now, the thing is, we need to check the minimum eccentricity condition. Now, previous case was a rectangular. Therefore, the eccentricity has been checked in both the direction. But now the case is a column in which one is sufficient. The eccentricity, minimum eccentricity is 1/500th of the unsupported length plus 1/30th of the diameter of the column. So substituting that one, we are getting that value as 19.93, and you can see which is less than 20 mm. Even if you want means you can check that one also should be less than 5% of the diameter, that is comes as 20 mm. So which satisfy the minimum eccentricity condition. Therefore, we can design the column as a short axially loaded one as per the IS Codal provision. Now, we need to go with the design of the longitudinal reinforcement. The same formula which has been applied in the previous case, we'll be applying it. But one difference, I'm sorry, this is not 1.05. Right. So, one difference is that here the column will be designed for spiral reinforcement or helical reinforcement. So, in that case, the load carrying capacity of the column will be increased by 5%, which is having high load carrying capacity. So, that is the reason we are multiplying this PU with 1.05. That is 5% increment. All other formula remains same as that what we followed in the previous problem. And this one is not that. You don't need to consider this one. Now substituting the values, here the factored load has been directly given. So we don't need to multiply with 1.5. So here 1.05, 0.4 in the grade of concrete is 25. And AG is the gross area of the column. Since it is a circular column, we are using pi d square by 4, where d is the diameter, 400 mm. So 0.67 into Fy is 415, 0.4 into FCK 25, and ASC, area of the steel for compression reinforcement. That is what we need to calculate. So on solving, we are getting ASC is 642 mm square. Now we are checking the minimum AST condition is 0.8% of the gross area, that is 0.8 by 100 into pi by 4 into 400 square, which comes as 1005 mm square. Whereas we calculated the requirement is 642 only. But in no case the ASC should be less than this value, that is a minimum percentage. So that is why we'll be designing the reinforcement that is providing, and since it is a circular column, we need to provide a minimum of 6 numbers. So 6 numbers of 16 mm dia bars are provided as the longitudinal reinforcement, which provides an ASC of ASC. It's not AST, sorry, it should be ASC, compression reinforcement. So ASC provided will be 1206. That is more than this one, the minimum AST requirement. Now moving on with the design of helical reinforcement. Unlike the previous case where the lateral ties will not be designed directly, the diameter and the spacing will be computed based on the codal provision. But going on with the helical reinforcement, we need to design this one based on some conditions. So assuming a clear cover of 40 mm over these spirals, the core diameter will be calculated. That is, we have a circular column, and in which we are providing the reinforcement. That is, sorry, the main reinforcement as well as the spiral. So here we are providing the clear cover of 40 on either side. So the core is nothing like from inner to inner. Sorry, from inner to inner. This is what is the core. So total is 400 dia. So 400 minus this is 40 and this is 40. Therefore, we will be getting 320 mm is the core dia. Now, assuming a bar diameter of 6 mm, that is the helical reinforcement, and the pitch ST should be calculated as per the class 39.4.1 of IS 456-2000, in which the condition has been given as volume of the helical reinforcement to the volume of the core should not be less than 0.36 times the ratio between the gross area and the area of the concrete minus 1 into the ratio between the grade of concrete and the grade of steel. Now, the volume of the helical reinforcement to be calculated, which is nothing like the area of the bar, pi by 4 into 6 square, into the perimeter, right? The perimeter is pi into 320 is the core dia that we have calculated, and now we need to find it with respect to the lateral ties. So, the lateral ties, which is being given as 6 mm, on both the sides 6 mm will be there, that is 6 by 2 minus 6 by 2 will be getting 6, right? And this has been calculated over a spacing of ST. That is why divided by ST has been provided. And this should be not be less than this condition. 0.36 into gross area is pi into the core dia, right? A core dia which is 320 square divided by 4. I'm sorry, this should be, it's not 400 divided by the core area. That is pi by 4 into 320 square minus 1 into grade of concrete is 25 and grade of steel is 415. On solving this one, we are getting the value as the ST, which will be coming in the denominator, which will be moving on to the other side. In that case, ST should not be greater than 28.4 mm. Now, they are given conditions for the spacing of the ties. As per the IS 456-2000, the spacing of the spiral reinforcement should be less than these two conditions. One is 75 mm and other one is 1/6 of the core diameter, the minimum of these two conditions. So here the core diameter is 320 mm. So 1/6 will give 53.33. And the spacing should not be, it should be greater than these two conditions. One is 25 mm and the second one is 3 times the diameter of the helical reinforcement. So here we provided 6 mm dia bar. So in that case 3 into 6, which will be 18. So what is the condition that we are going to use is the spiral's diameter should be greater than 18 mm, right? And it should be less than 53.33 mm. So what we calculated is 28.4 mm, right? So which is within the permissible limit of 18 to 53.33 mm. Therefore, we can provide the spacing of the ties as 28 mm. So provide 6 mm dia spirals at a 28 mm centers throughout the length of the column, right? So this is the reinforcement details. The diameter of the column is 400 mm, which has been provided with the 6 numbers of 16 mm dia bars equally or uniformly spaced along the periphery. And then the spirals being provided, which is 6 mm dia, spacing is being given as 28 mm with a clear cover of 40 mm. So this is what is the pitch which has been designed. So the distance between two consecutive spirals, which is 28 mm. And this is what is the main reinforcement once if you are seeing the longitudinal view. And this is what is the spirals. So to conclude today's lecture, we have designed or we classified the columns based on different conditions, and regarding the slenderness ratio which was being taken in most of the conditions, if that slenderness ratio is less than 12, the column will be designed as a short column, and if it is more than 12, it will be designed as a long column. And column will be subjected to 3 types of loading. One is axially loaded one, and second one is uniaxial bending, and the third one is biaxial bending. And today's lecture being covered with the axially loaded column. Even though axially loaded, the column will be checked for the minimum eccentricity conditions. Then only the Codal provision can be taken, and then the longitudinal reinforcements will be designed. And finally, we'll be designing the transverse reinforcement either in the form of lateral ties or helical reinforcements in the form of spirals. So this spiral columns offer better confinement and ductility. In the next lecture, we'll move on to the eccentrically loaded columns. Thank you.